Hey, good morning, everyone. Today, I would like to start the chapter on sound. And it may seem strange that I'm using PowerPoint today, but rest assured, I will go back to the chalkboard and talk about it in a moment. And the reason I'm using the PowerPoint is because there are some pictures, some tables that I would like to just show here that I wouldn't be able to do justice to by drawing on the board. So I'd like to take advantage of technology uh, and use that. So the chapter outline is as follows. So I'm going to talk about waves and types of waves again. So that'll be a little review. And then we'll talk about the characteristics of sound. And then we will talk furthermore about sound and intensity level of sound. We'll talk about the ear's response to loudness. And then we'll talk about vibrating columns and vibrating strings and air columns. We already started talking about standing waves on strings, but it doesn't hurt to review. We'll also talk about interference of sound waves and beats, and then finally the Doppler effect, which is basically if you have experienced the Doppler effect when you see a siren coming towards you or away from you versus when it's standing still. You hear when it's coming towards you, you hear a higher pitch, and when it's going away from you, you hear a lower pitch of sound. Okay, let's start with review of waves. So a wave, if you remember, is a disturbance that propagates from one place to another. And the easiest waves that we can visualize are transverse waves, which were basically mostly electromagnetic waves. And in everyday life, that you can see, if you just shake a string, when it vibrates up and down, you create a wave that moves, let's say, left and right, as represented in the image here. And to get a better visual of this, let's check out this simulation here from Penn State, where we have, look at this wave, the bumps are moving to the right, but look at the individual particles. Just focus on any of the dark dots, any dot. Any of the dots is just, all the dots are moving up and down, but their motion up and down creates a wave that's moving to the right or to the left. So the motion of the individual dots up and down is perpendicular to the motion of the wave. In this case, it's to the right. So up and down is perpendicular to the right. Okay. And I gave you the link here if you want to go to this uh, to the. It just shows you exactly the same thing I'm doing here, but just for reference. If you want to go back to the link, you can check it out. So these waves are called transverse when the motion of particles is perpendicular to the motion of the wave. Sound waves are actually not transverse, they are longitudinal. So as I speak, I cause air compressions. I cause the air to compress or depress in certain areas and cause propagation of the wave. So you have a loudspeaker that has a little diaphragm or a drum that moves forward and backward and causes the air to also move forward and backward. And then when it reaches the eardrum in our ear, it causes the eardrum itself to shake. And then the rest is biology, which I will not attempt to explain. I will leave that for your biology, physiology, anatomy professors to do that. Okay. So all we need to know is sound waves are longitudinal waves. So here is a little simulation also from the same source earlier. So longitudinal, the motion of the individual particles is parallel to the wave or anti-parallel to it. So look at any of the red dots or the black dots. So the red dots, just for easy reference, just focus on one. You see that it's moving to the right, sometimes to the left, and the wave itself, where you have the clusters of particles, they're moving to the right. So the wave is moving to the right, the particles moving left and right. So it's parallel or anti-parallel to the motion. Compare that with the transverse waves, where the motion of the particles was up and down and the wave was moving to the right. And if you combine up and down, left and right, you can get water waves. So just before we go to water waves, just for completeness, we don't need them. A slinky, in a slinky, if you have a slinky that's long enough, you can generate a longitudinal wave, okay? Where it is places where there is high density, places where there is lower density. Water waves are a combination of up and down and left and right motion. Look at any of the particles at the top. You have a wave moving to the right? The peaks are moving to the right. However, the individual particles, they're making little circles. I mean, how do you make a circle? You go to the left. I mean, for example, if you start at the top of the circle, you're going down and to the right until you reach the first quarter, and then you keep going down and then to the left. And then when you reach the bottom of the circle, you go left and then up. And then when you reach the left side of the circle, you will go up and then to the right, and then you have completed one circle. So it's a combination of longitudinal and transverse waves. We won't deal with water waves, but I just put it here for completeness. So a wave is usually characterized with a wavelength, a particular wavelength, which is the distance over which the wave repeats itself. It has a period, which is the time for one wavelength to pass a particular point. So if you look at a wave, it's like a train passing by you. So each time a cart passes by, that's a wavelength, and the time it takes one cart, the next cart to pass by you is called the period. And so, and also just furthermore, the frequency is just defined as to be as 1 over the period. And just the speed of the wave, how do you calculate the speed of anything? By definition, the average speed is distance over time. If the speed is constant, it's simply the instantaneous. So anyways, the speed is the distance over the time. The distance traveled, well, you travel one wavelength in one period. So the distance traveled is lambda, which is the wavelength. The period is capital T, so lambda over T will be the speed. But 1 over T, we just called it the frequency. So lambda times the frequency will be the speed of the wave. The units, of course, for the wavelength are meters. The units for period, well, it's a time, so the standard units will be seconds. Frequency is 1 over time, so it's 1 over seconds or hertz. And the speed is distance over time, so meters per second. Okay. So how does a sound wave look like? So if you think of the individual air particles as the little dots here in the picture, so where there are many dots clustered together, that's high density because it's more dense, right? More particles are closer to each other. And where they are farther apart, that's low density. So if you look at the density variation in the graph here labeled as B, the peak is where there is high density, and the trough, or the bottom of the minimum, is where there is low density. And so there is high density, low density, high density, low density. So from high density to low density, from high density to high density, that's peak to peak, that's one wavelength. And you can think of it as the pressure variation also. So where there is high density, there is high pressure. When there is low density, there is low pressure. Okay. So long story short, sound is a wave, and it's a longitudinal wave. And it's characterized by a certain speed and a certain wavelength. So what is the speed of sound? The speed of sound depends on it depends on the temperature, it depends on the pressure, and it depends on the material. And so it's kind of complicated. So you simply have to do measurements to figure it out. So for example, the speed of sound in aluminum is 6420, so 6420 meters per second. In granite, it's about 6,000 meters per second. Remember, the speed of light is what, 3 times 10 to the 8, 300 million meters per second. So the speed of sound is just a few thousand, whereas the speed of light is a few hundred million meters per second. So anyways, so the speed of sound is in the thousands of meters per second. In air, it's, look at here, the second row from the bottom. In air at 20 degrees Celsius, it's 343 meters per second. We will get familiar with this. You will remember this number from now on. I will provide it for you, but you will use it enough that you will remember it. You will see. For air at 0 degrees Celsius, it's 331 meters per second. In general, for air, there is a formula that you can use to calculate the speed of sound in air, approximately. And that formula is listed here in the third bullet point, where I say in air, the speed of sound is given by V equals to 331 plus 0.6 times T. T here, capital T, is the temperature. So from the context, you're supposed to tell whether we're talking about T to be the temperature, or T, we're talking about the period, or T, we're talking about the tension. So there is no tension or period here. It's the speed of sound in air. So it should be clear from the context. If you're not sure, ask whether T is temperature or period, if you're not sure. Anyways, it's 331 plus 0.6 times capital T. So let's say at room temperature, it's 20 degrees Celsius. So you have 331 plus 0.6 times the temperature, which is 20. So 0.6 times 20 is how much? Well, 0.6 times 10 is 6. So 0.6 times 20 is 12. And so 331 plus 12, that's 343. And so the speed of sound in air at 20 degrees Celsius is 343, as indicated in the table as well. And if you put the temperature to be 0 degrees Celsius, well, 331 plus 0 times plus 0.6 times 0, that's 331. Okay. All right. What are some of the things we know about sound? So what do we know about sound? We know a few things. Biologists know a lot more, and physiologists and people who specialize in hearing, they know much more than this. So as far as we're concerned, we hear sound levels between 20 hertz of frequency, of 20 hertz to 20,000 hertz, and frequencies that are greater than 20,000 hertz, they're called ultrasonic, and frequencies that are lower than 20 hertz, they're called infrasonic, and we don't hear them. And by the way, this range 20 to 20,000 hertz deteriorates as we age. So you might some people might hear up to maybe 10,000 hertz only, instead all the way to 20,000 hertz. So the higher frequencies you tend to lose. So you get, if it's larger than 20,000, it's called ultrasonic. If it's lower than 20,000, it's called infrasonic. You probably heard of ultrasonic waves or ultrasound, which is used in medicine, for example, to look at during pregnancy. They use ultrasound. And infrasound is used by certain animals to communicate with each other. For example, elephants and whales. In part, they communicate with infrasonic waves. Okay, so that's just general. You don't have to memorize any of this. Yeah, I mean, this is just for curiosity. So let's just take a look here. It says 5 seconds after a brilliant flash of lightning, thunder shakes the house. So you see lightning and then you hear thunder. Why? Well, lightning is lightning. It's light. It travels at the speed of light. So you see it pretty much instantaneously. It takes a fraction of a second, but it's a lot faster than the thunder, which is the sound you hear. Sound travels at the speed of sound. Lightning travels at the speed of light, which is many more times higher. As you remember, I said speed of sound is 3 times 10 to the 8, whereas the speed of light is 3 times 10 to the 8 meters per second. The speed of sound is about 343. So it's about 1,000,000 times more. It's a lot quicker. Um, so let's say you see lightning and then you hear thunder 5 seconds later. So you see lightning, 5 seconds later you hear thunder. Was the lightning a mile away, much closer than a mile, or much farther than a mile? What do you think? Just think about it. Just pause here and think about it. And remember, thunder travels at the speed of sound. In air, it's about 343 meters per second. So every second, it travels 343 meters. So in 5 seconds, how far does it travel? Well, that's 343 times 5. So that's about 300 times 5, that's 1500, or maybe closer to maybe 1700 meters. A mile is about 1600 meters. So it's about a mile, yeah. So it's about a mile. Not much farther, not much closer. So just about a mile. So if you see lightning and then you count like 1, 2, try to be as approximate close to 1 second as possible. You can tell where the lightning struck. Okay, so it's closer to about a mile. We talked about intensity. This is also a review in the previous chapter, and we said, first of all, remember energy was the amount of work that you do, or it is measured in joules. The power is how much work do you do per unit of time. And so not just how much energy you're expending, but how quickly are you giving off the energy? How quickly do you burn through it? And then the intensity takes that concept further and it says how much energy passes by a certain area, an area A, per unit of time. So it's the energy per unit of area per unit of time. The energy per unit of time is power, so E divided by T, that's the P part, the power. And so you just have P over A, that's called the intensity. So intensity, if we can define it as the power per unit of area. Remember, power is energy per unit of time, so that's joules per second, which we call watts, W. Area is in meters squared, or square meters. So intensity, which is power over area, so that's watts per square meter. So when you move away from an object, right, because it's the power per unit of area, so if you have a point object that's emitting power, that's emitting energy per unit of time, then it has an intensity. The farther away you are, the less intensity you feel. Because recall with the fire hydrant example I gave you when I talked about intensity. If you have a fire hydrant that's sprinkling water in every direction, if you're really close to it, you get sprinkled by a lot of water. If you go away, farther away, you will get sprinkled by fewer drops. Not because the sprinkler is emitting less water when you go farther. It's emitting the same amount of water per unit of time. So it's the same power. However, when you move farther, the surface area through which the water is spread is larger. So the intensity gets larger. And bats communicate, or they can use this to locate objects. They can tell based on the sound, decrease in sound intensity, they can locate small objects in the dark. So anyways, again, intensity is power over area. And so if you have a source, a point source that's emitting sound in every direction or emitting energy in every direction, then the intensity will be the power over the area. But what is the area? Well, if you're emitting, again, back to my fire hydrant, it's emitting everywhere in every direction. So if you draw a big circle around, a big sphere around it, the water droplets are spread over the area of that sphere. They're hitting every part of the sphere. If you make the sphere larger by moving away, the droplets per unit of area become less because the surface area gets larger. What's the surface area of a sphere? You can review that from your math class. It's 4 pi r squared. That's the surface area of a sphere. Remember, a circle is pi r squared. A sphere is 4 pi r squared as a surface. So in other words, if you take, for example, like a plastic ball, like those cheap ones from the dollar store, what do we mean by the surface area? If you take the ball and you want to measure the surface area of the ball. So if you take a pair of scissors, and you cut the ball and kind of open that area, open the ball, the plastic, and ask how many square inches is that? What is it? Well, you can measure it that way, or you can just tell if you have the radius, it's 4 pi r squared. That would be the square footage or the square inches or square meters of that. Okay, so that is the sound intensity. When we talk about sound, however, we like to talk about the sound intensity level because it's a more convenient scale. It's called beta. So the intensity is I, sound intensity level is called beta. So if you look, and it's on a logarithmic scale, I will tell you in a moment why that is. So it says if you listen to a variety of sounds, the sound seems to be twice as loud as another one if it is 10 times more intense. So if you make the intensity 10 times as large, if you increase the intensity tenfold, the sound seems to just double. And so we will define this in a logarithmic scale, and I will show you how to use this formula again on the board in a few moments. But right now I'm just doing the kind of some bookwork here and bookkeeping. Okay, so the sound intensity level is called decibels. It's a constructed scale. It's called beta, and it's 10 times the log, so log base 10 here. And I will review some of the properties of logs also. So log base 10 of I, the intensity of sound that you have, divided by some reference intensity, I0. And I0 is taken to be the faintest or the least sound that's detectable to the human ear. So what is that sound? Yeah, it's an experimental thing that you can do. And people came up with a value of measured of I0 to be 10 to the minus 12 watts per square meter. So an intensity of 10 to the minus 12 watts per square meter is the least intensity that we can hear. I'll show you a chart in a moment. So remember, I want to also convince you why we use the log scale. In addition to the fact that when you double the intensity, when you increase the intensity tenfold, the sound level seems to only double. So we will see in the next slide here, or the next two slides. So beta is called the bell, and the unit that we use is the decibel. Okay. So it says here the intensity of sound doubles each time you increase the intensity level by a factor by 10 decibels, and we will also see why this is the case. Okay. So here are some. Here is a table here from our book, Giancoli, 12-12. So it says here source of the sound, and then it gives you the sound level in decibels, and then the sound intensity in watts per square meter, the corresponding one. So for example, a jet plane at 30 meters away from you can give you a sound intensity level of 120 decibels, and the intensity is 100 watts per square meter. The threshold of pain, sound, like if it's 120 decibels or intensity of 1 watt per square meter, that's painful to the ear. If you have a siren at 30 meters, the intensity level is 100. It's very loud, which corresponds to only 10 to the minus 2 watts per square meter for the intensity. So the sound level is beta, and then the intensity is 10 to the minus 2. So if you're in a normal conversation with somebody, that's 65, an intense sound level of 65, and the intensity itself is 3 times 10 to the minus 6. And someone whispers, the intense sound level is 30, and the intensity is 10 to the minus 9. And then the threshold of hearing, the sound level is 0, and the intensity is 10 to the minus 12. Remember, you can measure this, and the threshold of hearing turns out to be 10 to the minus 12 watts per square meter. The sound level, the reason it was defined the way it was defined we use that reference intensity to be 10 to the minus 12, so that when the intensity itself is 10 to the minus 12, the sound level will be 0. It's a nice scale. Now, look at the scale itself, and you will see why we use logarithmic scale. Look at the intensities. From a jet plane, which is 100, 10 to the 2, and the threshold of hearing is 10 to the minus 12, that's a range of 10 to the 14, or 10 to the 14, which is very large. So there's 100 trillion. Not a very convenient scale, at least to the regular person. You will, to the average person, you can't really tell. But when you tell a person sound level is 10 or 20 or 30 or 50 or 140, a nice scale from, let's say, 0 to 120, the threshold of hearing, they can relate to it. But when you say 100 or 10 to the minus 12, not everyone could relate to it, unless you're taking physics 120, right? Just joking. I mean, if you're a science person, you will see we deal with powers of 10 all the time, but not a very convenient scale if you're talking to, let's say, your child. All right, if you're talking to a younger person trying to explain sound level, if you tell them it's 10, if it's really quiet or very loud, to be 100 or 120, that's a convenient scale. So here are some interesting facts. The loudest sound produced in a lab has an intensity of 10 to the 9, so that's a billion watts per square meter, and the sound intensity level is 210 decibels. That's well beyond. So if you want to know, the threshold of pain is 120, so how much does it take it to rupture a person's eardrum? Well, okay, so if it's painful at 120, a jet plane taking off is 140, beyond painful. So if you increase the sound level to 160 decibels, that's well below the 210, the loudest produced in a lab. So at a sound level of beta equal to 160 decibels, it will likely rupture the eardrum. I say likely because, well, not everyone is exactly the same. But on average, a person's eardrum will rupture at intensity level of 160. The corresponding intensity is 10 to the 4 watts per square meter. And one of the goals of this chapter is to be able to go back and forth from beta to I and I to beta. So how do I go from I equal 10 to the 9 in the loudest sound produced in a lab to a beta equal to 210? Or knowing a sound level of 160, how do I calculate I to be 10 to the 4? That's the logarithmic relationship, and we will get familiar with it very soon. All right, so now we will go to the lecture part, to the blackboard.